Okay, hello everyone. So my name is Thomas, and today I will present TLSNotary to you. So TLSNotary, the title is Make Web Data Provable. And before we have a look at what TLSNotary does, let's first have a look at the organizations behind. So TLSNotary is a project inside of Privacy and Scaling Explorations, and Privacy and Scaling Explorations, or PSE, is inside the Ethereum Foundation. And what PSE, so it's a sub-team, and what we do is basically like make cryptography like easily usable for developers, like open source it, and also some applied research. And yeah, TLSNotary is one project inside of PSE. Okay, so first we should probably make clear what TLSNotary tries to solve. So what's TLSNotary? So it solves the problem of the portability of web data. So think about, for example, you're Alice now and you're going to visit some website. So then you're probably using the HTTPS protocol and you get some data. So now what you currently cannot do is like forward this data to some other party, in this example Bob, in some sort of cryptographically verifiable way. Right? Think about you could do some screenshot and so on, but yeah, so there's not really a reason why Bob should trust you, right? On the other hand, there are quite a lot of use cases why this might be interesting or why you might want to do that. So, for example, think about your government has some data about you, and maybe you want to use that to go to some KYC provider and use it there. Or same with banks. Banks have like some information about you, maybe about your I don't know, credibility score or something like this, and you want to get a loan from some other creditor, so you would like to use this score there. There are many, many use cases. Also think about like just proving you own some social account, Reddit, Twitter, or even maybe you want to prove that you you want to like help the Internet Archive scraping for some data, and you would like to attach a proof that this is really the website that you found, right? Or even in Web3, you maybe you want to trigger some smart contract function, but dependent on some valid input from Web2, right? So, yeah, it would be nice if this is possible. So let's first have a look at the internet today, right? So nowadays you have basically the TCP/IP stack, which ensures that you are like connected to some computer that administers the connection and meters the data flow. And on top of that, you have this TLS, transport layer security protocol, and that's, so to say, the cryptography layer of the web, and this ensures two things. So the first one is authenticity. That basically means that the data you are sent and the data you are sending out has not been tampered with in transit. The other thing is confidentiality, that it's encrypted, what you send and receive. So when you go to some website, you're probably using HTTPS, which is just HTTP together with TLS. I think it's, I don't know, 95 or probably 99% of the servers support that nowadays. Right, so coming back to what I said in the beginning, you have this authenticity and confidentiality, but what you don't have is portability of data. There's a cryptographic term for that, which is called non-repudiation. So Bob has no reason to believe that the data Alice sent to him is really coming from the website or just made up by her. And the reason for that is that in TLS, the keys you use to encrypt the data, they are symmetric keys. That means if you have a look here, the yellow keys, Alice basically has the same key the website uses for sending out the data, like encrypting it and creating authentication tags. So what she could do is she could just come up with some data and then just encrypt and create the tag herself for these data and then send it to Bob. And there's no way for him to differentiate between those two scenarios. Okay, so how can we fix this? Welcome to the bright world of TLSNotary. So when you use TLSNotary, you get also authenticity and confidentiality. But what you yeah, you get some sort of like many other things also on top. So if we have a look at the picture, we'll see here that Alice is still connected via TLS with the website, and there's something like going on between Alice and Bob in the back operating this TLSNotary protocol. So what you get now is authenticity, confidentiality, and now also this portability of data. But it's not only portability, like forwarding it in a credible way, you also get some like, yeah, like some sort of privacy or like control of what you want to show to Bob in this case. So for example, you can do some selective disclosure where you only show some parts of the server response or so. And you can also do like ZK proofs on the data. So for example, like think about it, like you just want to prove you're over 18 without disclosing anything else coming from a government server. So just simple example. Okay. And if you have used TLSNotary in this kind of setup where Alice is the prover and Bob is the verifier, there is no trust assumption. Alice simply proves some assertions about the data. What's nice about it is also that it's invisible to the website. So if you look at the picture for the website, it just looks like an ordinary TLS connection. And this is quite nice. So we see that there's no way for the website to really differentiate between if TLSNotary is now run in the back or not. And this also means that, yeah, so when you use TLSNotary, there's no, like, you don't need to change TLS in any way. Right, you can use the current deployment of TLS, which is quite nice, because changing such a standard probably takes decades if you even succeed. All right, okay. So before we now have a look at how TLSNotary achieves this portability of web data, let's have a look at some other solutions. So basically, there are like 3 solutions to this problem, and the first one, which is also the most elegant solution or straightforward, is just signing the data at the source. So think of, you have some web server and you could now sign the data. You could either like change or adapt TLS to do that, but you could also do it on the application layer. I think there's an RFC for this in HTTP, which is called I think SXG, which is just basically like hash the response and then sign it. So this is in some sense like the right solution, but there are some problems with this because it requires the website to implement this. And yeah, there are some like business models which rely on that, that they have basically the sovereignty over the data. Wow, yeah. So this is it's a problem. So there is some disincentive to adopt that or to do that. So what you could also do is use OAuth protocol, and then we would just delegate the access. So if I go to some website, the website requires some data about me, then I can send it to some data provider and then authorize the data provider to forward data from myself to this website, right? But yeah, there are problems. So first now the data provider knows exactly what you're going to do with your data, and if he doesn't like it, maybe he wants to censor you or like doesn't allow it. Also, the website needs to implement it. Yeah. And the last thing you can do is the proxy approach. So if you have a look at this picture, what you could do is, well, you would move Bob, the verifier, in between Alice and the website. And then you would send the requests to Bob, and Bob forwards them to the website responds, and Bob sends back a response to Alice. So the nice thing is that, the website doesn't have to cooperate in this case. But you run into other problems here, because now Bob is basically the proxy and always uses the same IP, so it's easily to block at scale. And also, your protocol gets some other like security assumption which rely on the network topology. Like think about if Alice, for example, wants to prove something, but she is like an internet service provider who controls the network topology in some way, she can maybe sneak herself again in between the proxy and the website. So you run into problems with that. And also, even if it's only encrypted traffic you send through the proxy and then do a zero knowledge proof afterwards, you still have that, like the proxy knows to which website or server the data are sent because it has to forward it. So this is like what you can do in maybe the solutions which directly come to your mind. Now we have a look at TLSNotary. So TLSNotary uses an entirely cryptographic approach to this problem, and that is multi-party computation. So multi-party computation is if you have two parties or like even several parties, and each of them has some sort of secret input, and they want to compute a function which is like the output of on these secret inputs. So like Alice has an input X, Bob input Y. This should remain private during and after the computation, and like you compute a function on that, and this should be public, or maybe only returned to one of the parties or subset. That's also possible. Yeah, and this is exactly what TLSNotary does. So Alice is connected via TLS with the website, and in the back she runs this MPC TLS connection together with Bob. You can think about like that they in some sense do what is necessary for TLS together as the client now split between two parties, and they compute everything together, like the key exchange, the request encryption, response decryption, all that kind of stuff is now done in MPC. That's basically the idea how it works. All right. So this was like the general introduction from like the bird's eye view to the problem. And now I want to go a little bit more into the detail. So like for the remaining part of this talk, we have like basically two chapters. The first one is like a little bit about the techniques and cryptography involved. And then we'll have a look at the phases of the protocol. So for the techniques, we have oblivious transfer, which is some like of general like some construction which is used or which is necessary for all other protocols we are using. So specifically garbled circuits for like general MPC computations. For binary stuff, then we have this OLI or VOLI, we'll come to that in a minute, for computing, doing computations which with larger prime fields. And then also we have to run some interactive zero knowledge protocol in the end. We'll have a short look at what that does. And for TLSNotary, we start with some pre-processing phase. That's basically doing computation before the connection is online. And then you have the TLS phases, like you have the key exchange. Then you have the pseudo-random function to stretch the pre-master secret to the master secret. And then you have the actual traffic phase, like encryption of requests, sending out and getting server responses, decrypting them. And in the end, we'll have to do some proving. Okay, so I suggest let's first start with the techniques and have a look at oblivious transfer. So what is oblivious transfer? High level, what's the idea of the functionality? Like you have a sender and a receiver. The sender has two messages, M0 and M1, and the receiver has a selection bit C, which is either 0 or 1. And now basically PS sends M0 and M1 in a way, I say in a way because that's important, to PR, so that PR only learns the message which belongs to his selection bit. So if C is 1, M, he will only get M1 and vice versa. And PS will learn nothing, especially not the selection bit. And if you think about it, you need cryptography to implement that. Especially you need public key cryptography for that. And there are different variants of that. So this is what I just showed here to you is one out of two oblivious transfer. There is random OT, where the messages and the selection bits cannot be like chosen by the parties. There's correlated OT, where these messages have some sort of correlation. And this we will see in a minute where we'll need this. But think about this as a basic building block inside of TLSNotary, which is basically used nearly everywhere. Okay. So now we have had a look at OT, so now we need to talk about garbled circuits. So garbled circuits is a general purpose MPC protocol. So that means you can compute any function with it. And especially you want to use it if you are like in a binary context. Think about like a binary, just 0 and 1, because then it's pretty efficient. So especially we don't use that for large prime fields because then it becomes very inefficient. So in its general purpose, you can compute any function with it. And what's especially nice about garbled circuits is that, so usually when you do MPC, I mean, there are other ways to do MPC. The problem is that most or many protocols are not very efficient because you have many like messages sent around. And the number of messages you have to send around depends on the function or on the circuit depth, so to say. And this is not true for garbled circuits. And this is very nice, so it gives you some like nice performance, right? Because you send something in the beginning and you send something in the end, and that's it. Yeah. So, okay, how does this work? We have two parties, the garbler and the evaluator. So each of them have some sort of secret input, xg and ye, and again, compute some function on that. So, okay, I think to get this from a high-level perspective, we need to think about as the function as basically as like a circuit. Think about XOR or AND gates, right? And then you have like many gates in a circuit. Like think about your circuit as an array of gates, and every gate, think of it as a truth table. So for example, an AND gate, yeah, you have like this truth table would basically for an AND gate consist of 0, 0, 0, 1, right? And you have 4 rows, and depending on the row is basically determined by like if the input is 0, 0, then you get a 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. That's basically, you get the idea. So from there, we go now to a gate with wire labels, and you can think about these wire labels just as some sort of random strings, right? So we will see that the garbler will garble, we say he garbles the circuit. That means like he will do something with this circuit, and what he will do is like he will come up with these wire labels. And think about now not 0 and 1 flowing through the circuit, but these random wire labels, and only the garbler now knows which wire label belongs to either 0 or which wire label belongs to 1. This especially means that an AND gate here and an AND gate there in the circuit don't have the same truth table. Yeah? So, right, now the evaluator already doesn't know which values flow through the circuit, but now we have to do one more thing. We have to like encrypt it, so that basically the evaluator can only like evaluate the circuit on the correct path, which is like dictated by the choice of inputs, right? So for example, this especially means for an AND gate, let's just focus on the first row. You would like encrypt the wire label belonging to the clear value 0 with a wire label flowing in I and j belonging both to the clear values of the row. And you do that for all the 4 rows basically, and then you have, so to say, a garbled gate, right? And then think about the circuit as like a huge array of these garbled gates. And basically that's it. So now what does the garbler do? Now the garbler, he garbled the circuits, he sends over all these like encrypted or garbled gates to the evaluator. Then he sends over his active input labels, the WI, because remember, like only he knows if they belong to either 0 or 1. The evaluator, for him, it's just like random. And now the question is, how does the evaluator get his own input labels? Because remember, we have a function. The garbler has some input to the function, but also the evaluator, right? And here you need then oblivious transfer for this, so that the evaluator basically gets his input wire labels without the garbler learning the clear values behind it. And that's it. Then the evaluator will start basically with a first input layer of the circuit and like work himself through the circuit, doing decrypting gate by gate on the right path through it. And in the end, he will arrive at the active output wire labels, right? Still the 128-bit like random numbers. So what do we do now? Now we come basically to the output decoding phase. And what happens here is now it depends on who should learn the output of this function. So what you can do is you can send the decoding information, which is the mapping from wire labels to clear values, can send that to the evaluator, then the evaluator will learn the output, or you can basically have the evaluator send his active output labels back to the gabler, and then the gabler will learn it, and if you do both parties learn it. And this is like the gist of behind garbled circuits, how it works. So what I should say is, let's say, for example, you want to garble an AES circuit. So you have to do all of this per one evaluation, right? So if you want like compute an AES again on some different input, you have to garble all of that again. So this is not FHE, right? It's different. Okay. So, and because you have to do all of this again and again, like think of, we have many circuits in TLSNotary with many more gates. So we want to have this as efficient as possible. And there are some optimizations you can use for it. I don't go into the details here, but think about like going from, if you think about one gate with this truth table, like 4 rows, you can get down to 2 rows. Yeah, so there are these techniques which are called row reduction and half gates. You get to 2 rows with 3 XOR. You basically even don't have to send XOR gates to the evaluator. You can just so to say incorporate them. And there's even something you can do to improve the performance of your garbling by using a fixed key AES cipher. So again, this is used whenever we want to compute something in a binary field. This means especially AES and SHA. Okay. That's it for garbled circuits. So now we have a problem because, I mean, we've done now, like, we have a tool for general purpose MPC for binary fields. But if you think about TLS, for example, the key exchange, there's also like, there are big prime fields involved because you deal with elliptic curves. So what do we do here? That's where oblivious linear evaluation or OLE comes into play. And you can think about it as a tool to like compute with these big numbers and prime fields efficiently in a way. So you have again 2 parties, PA and PB, and they have their inputs A and B. These are like from elements of a big prime field. And what you get out is this X and Y. Sometimes X can also be the input, but yeah, let's not focus on that here. What you get is the output in such a way that it fulfills this equation, so that you have like y is equal to A times B plus X. And if you rearrange that, you arrive at y minus x is equal to A times B, or y plus minus x is equal to A times B. And that's why this is also called like M to A. You should think about it like you can basically convert your multiplication into an addition, right? And if you now also have the vice versa as a building block, which is called A to M, like going from an addition to a multiplication, you have to think about, like, you have to some big equation, and by using either M to A and A to M iteratively on this equation, you can basically shrink it down to into some result. And that's exactly what we do. Whenever like we are forced to deal with big prime fields, we're using these two to do computation. Yeah, and they also play a big role in our interactive zero-knowledge protocol. So especially as a vectorized version of it, which is called VOLI. Yeah, that's basically like, think about just doing this several times, but the B is fixed. All right, and in a way, that's like the big building blocks we use in TLSNotary, like from the conceptual idea. So now we can have a look at TLSNotary, what it does, and yeah, like, okay, pre-processing. So what is pre-processing? So when you have like, we're doing multi-party computation, and that's like takes a lot of time to do the computation, right? But you have to remember, I mean, there is a server waiting for requests and responses. And many server implement some sort of cutoff. So if they don't get like an answer in like, I think a minute or whatever, they just shut down the connection. So what you want to do is like not run into that, and that's why you move all the parts of your computation, you can move into an offline phase before the online phase. Yeah, and that's what pre-processing is about. So first we ask the developer to specify the expected traffic amount. So we have these values, max send, max receive online. And that's basically, we ask you, tell us how many bytes you're expecting to send to the server and how many bytes are basically, are you expecting the server to respond. And based on that, we do like the pre-processing, because we need some sort of gauge of, like how much do we need to pre-process. And if we know that, we'll start our OT machinery. Like, remember from before, OT, very important, needed nearly everywhere. So there's a problem with OT. So like, OT can only be done with public key cryptography. And public key cryptography is, like, considering the time it takes or the performance, not that great. Now we need many OTs, like think of millions. So what you can do now is basically use some sort of base amount of real OTs and then do like a blow up, like an increase the number, like think of, you start with 100 real OTs, and then if you use an OT extension, you can get like thousands of OTs from these bootstrap OTs. Okay. And that's what we do here. So we use like CO15 as a protocol for our base OTs. It uses elliptic curves. And then we use an OT extension COS15, which is, it's just like a random Oracle model protocol. It helps basically to like, it uses symmetric key cryptography to like get many OTs from that. And that's why it works, because the extension works without public key cryptography, so that's very efficient. And we use this OT extension then nearly everywhere in our protocol, except for our interactive zero-knowledge protocol, because that's even more OT hungry, and there we need like think of a much more powerful OT extension. And there we use the ferret protocol, which is based on learning parity with noise assumption. Okay, so now we have run our OT machinery. So now the prover, because we already know roughly what's the expected traffic amount, now the prover can garble all the circuits and send them to the notary. So this is especially the encryption and decryption circuits for the traffic, but also the PRF circuit, and there's also a small garbled circuit involved in key exchange. And we also prepare our interactive zero-knowledge protocol. Okay, so now we are in the key exchange. How does this work? So the general idea here is, so in TLS you just have client-server, and the easiest picture to think about this is to split now the client between prover and verifier, right? And this is also the exact reason, in some sense, why TLSNotary works, because you split the client key between prover and verifier. Now the prover hasn't the full key anymore, so that means especially that Alice cannot like encrypt or decrypt anything without Bob, right? So that means like she cannot make up some traffic and like claim it would come from the server. That's the general idea of why and how it works. Okay, let's quickly go through here. So the verifier comes up with some ephemeral public key, sends it to the prover. The prover adds his public key to it and sends it to the server. Now the server can like derive the elliptic curve, what's it called, this ECDH secret, the pre-master secret. Right, then he also sends his public key over to the prover forwards it. So, and now prover and verifier each on their own can basically come up with an ECDH share of the secret. Now, these shares are just like shares under elliptic curve point addition, which is not ideal because remember we want like you have these like PMS shares under EC point addition, but what we would like to do is like we need to feed that in the PRF to get the master secret and ultimately the session keys. But if you remember, the PRF is SHA, basically SHA circuits in some sophisticated way, which is binary. So we'll use garbled circuits, but these are like big numbers. So what we do here is we compute, that's in this MPC box, we compute sharing, we go from this elliptic curve point sharing of keys just to a binary XOR sharing. And then we can feed it in the PRF to compute the session keys. Right. Okay, so now basically we have computed, like we have done this key exchange, then we have fed all this as an input into the PRF. The PRF, of course, computed with garbled circuits, like into PC. And now we arrived with the session secrets, right? So, and we can use them like now in the online traffic phase for the encryption and decryption. So how does it work? So the prover has CWK is client write key, and of course he knows the plain text he wants to send to the server. The verifier has his client write key share, and now they use it as an input for AES CTR. So maybe one thing. So the encryption and decryption in TLS is mostly AES GCM, so that's the most common cipher suite. I've put into this box AES CTR because AES GCM is like just normal AES CTR with some sort of authentication mechanism which is Ghash. And I don't want to go into the details of Ghash in this slide, so let's just focus on like what happens to the actual actual requests and responses. Yeah. So AES CTR is then here like executed between prover and verifier. Again, AES binary circuit. So we use garbled circuits to compute that between prover and verifier, and out pops the ciphertext. Ciphertext, both parties get it. Prover sends the ciphertext to the server, and verifier also gets the ciphertext. So for response decryption, it's kind of similar. So now you use the server write key share from the prover and verifier server write key share as an input. So the prover got the ciphertext from the server, then forwards it to the verifier, and they both supply it as a public input to the AES CTR circuit. Again, like garbled circuits, they decrypt it and they get a plain text, but no, sorry, not they, only the prover gets the plain text, because we want to hide it from the verifier because he shouldn't know the plain text. All right. There is an optimization you can do here, which is called deferred decryption. And that's basically if you only have like one request, one response, there is no reason to like decrypt the response in the online phase, because you can do it afterwards, and then you don't incur any MPC overhead on that, right? So why can you do that? And that's because after closing the TLS connection, that's pretty nice, the verifier has no secrets anymore. So think about these SWK and CWK. So after the connection is done, there's no reason to keep them secret anymore because the connection is closed. And that is quite nice because now we can use that and prove the correctness of our computations. So think about now, let me think about it. Okay. So first, so we prove now the correctness of the computation because the verifier has no secrets anymore. For that, we use an efficient interactive zero-knowledge protocol that is Quicksilver. And you have to think about it like from a high-level perspective, like we are gonna redo all the computations or all the garbled circuit computations from the online phase. But we do that like not in MPC, it's like you create these max, these MI, and you create the keys, KI, and you have to think about it like you create the max for the prover and the keys for the verifier, and they always fulfill this equation. And then the prover and the verifier works through the circuits of the online phase, and in a way, this is a check for the verifier to check if the prover like cheated or not. Because if everything is correct, then in the end, this equation will also hold on the circuit outputs. And that's the idea of how it works. I mean, this was a little bit simplified, but it's a general high-level idea. Right. So, and you do that for all garbled circuits computation in the online phase. And we also prove the knowledge of the clear text for the server responses for the prover. All right. So there's one thing you can do. You can decode the server write key for the verifier, which means like that's the key the server uses basically to encrypt the messages, and you can decode it already in the online phase if and only if you have no secrets. Or if you don't expect any secrets in the server response, and this gives you like it's more like efficient and gives you like a better and more easy commitment. But you can only do that if there are no secrets expected. All right, so that was basically the gist about how TLSNotary works. I mean, there are of course some more details, but that's the high-level idea. So where are we currently? So everything works quite nicely, I would say. We are in the moment like doing some performance improvements and adding additional features. So in the last few months, like, I don't know, the PRF was improved, and also like the number of round trips. So we are in this phase where developers reach out and ask us to implement some features. For example, in the last weeks, we added different commitment types. We also added support for mutual TLS, which is basically client authentication. And also in our notary server, we added JWT authentication. So think about like, we're in this phase where we're stabilizing, improving performance, and adding some features. And the next big point on the horizon for us is adding a plugin system to give developers some sort of fine-grained control of how exactly they want to run the prover, or how exactly in which environment and with which settings the verifier or notary should be run. So it will be some sort of plugin system. And also an on-chain verifier is still interesting. So think about that's this case where you want to use Web2 data to trigger something in a smart contract. Of course, the smart contract cannot participate in this MPC TLS connection. So you get a trust assumption there in the form of a notary. Yeah? And then it's still not like, it requires some more research of how to do that, because if you then have a verifier in a smart contract, it's still the question of how you like check the correctness of the certificate chain. So it's like ongoing research to some degree. And also we want to add support for TLS 1.3. Currently only 1.2 is supported. And I'm sure there are probably some other things which will pop up in the coming months. Yeah, thanks. So this is our team. I've put some links here, like our website and our documentation, which we definitely need to improve. And also links to some GitHub repositories, the core protocol, JavaScript bindings, and also our browser extension. Yeah, thanks. You do you say? I don't know. 6:26. Yeah. So yeah.
very much, but the verifier doesn't need to be online. He will provide his stuff and it will be later used.
I mean, it depends on how you operate it. So if you like, so basically, you can have a direct verifier, like I showed in all these pictures. Then it needs to be online because it participates in this MPC TLS phase, which is exactly at the same time where the connection is open to the server. What you can also do is like, you can sort of outsource that to some notary, and that's basically a server which does like, where you create commitments for this session or for the TLS session in some form, and this is signed by the notary and then returned to you. And then you can you can later use that then for some verifier. So these are basically the two modes you can do. But for this MPC TLS stuff, you need to be online. Yeah.
And do you have some users with some partners?
Yeah, there are some like some startups, I would say, which use TLSNotary to, I mean, yeah, for various use cases. Yeah.
Thomas, when you explained the proxy approach,
Mm-hmm.
I think you didn't want to say it, but that's what Reclaim does, right?
Yeah. Mm-hmm. We are also thinking about implementing this as a mode of operation.
Okay.
Yeah, because I mean, it's like it's just like it depends on what you. I mean, if you want to have like the best of security, you should probably do MPC. But if you maybe like, yeah, you're more interested in like performance, and honestly, there's not so much to lose in what we do, depending on the use case where you use it. It can be a viable alternative to use a proxy approach.
But isn't it, so if the MPC is between the client and the notary?
Yeah, well, yeah, the client is now the prover. Oh, sorry, can you say again?
The MPC computation is both done by the notary
Yeah.
and the
Prover.
prover.
Yeah.
So if I understand correctly, the prover is, I'm the user that's trying to prove that data.
Yeah.
And the other one is the TLSNotary, right?
Yeah.
Okay, so I have to trust that your notary is
Right. So
honest, right?
right. So if you, that's exactly the thing. So if you have a notary, then who basically helps you to create a commitment and then signs it, so that you get an attestation, which is later presentable at to some verifier. In this case, you have a trust assumption here.
Yeah.
But if you have like only a verifier, like there is like you directly prove something about the ciphertext, or like in this case, there's no trust assumption because the verifier, I mean, it has to trust himself. So, yeah.
Right. Okay. Yeah. No, I'm just coming from the point of view that in MPC, it's cool to have more players doing the computation than just two, like just in general.
Are you talking about like maybe having more like notaries in this? Yeah. So that was some topic quite some months ago. So the thing is, you can do garbled circuits with multiple parties, like not only two, you can, but it's like some sort of little bit esoteric. I mean, it's like, there are like papers about that, it works in theory, but it gets complicated, and also you always have to keep an eye on the performance. So it's
Right,
like, yeah.
Yeah, okay.
Yeah.
It would be cool to try to forge a proof if one of the MPC parties is not honest. To see actually like how hard it is, or how feasible it is to do.
Yeah. I mean,
Trying to compromise a notary to be like, I actually thought that.
we played a little bit with it, but this would be some sort of like an effort in its own, and there are like more important things currently, like, yeah.
Well, yeah, I'm a bit.
No, but it's definitely interesting, yeah.
Or also the other way, which is the origin server.
Sorry?
Or also another attack vector would be that the app server that's sending the data,
Yeah.
it would forge its own TLS certificate
Yeah, but I mean, then you need to fake the DNS. Yeah.
Something that like NSA could do. Maybe.
Maybe.
Yeah.
And the computation, where does it actually happen? In the prover or verifier or whatever, etc.?
Yeah, so I mean, the heavy computation part is on the parties who are involved in this MPC TLS connection, and that would be prover and verifier, yeah, or prover and notary. And then if you later present the proof to some verifier, this way verifier has not to do the MPC TLS part, but yeah, still there's some computation and verification to do, which makes it hard to run in a smart contract. So, but the majority of computation is the MPC TLS stuff. Yeah, I guess that's it. Thanks.